All right, I'll start then on this. Analogues of Koska numbers. I think it's just completely amazing, actually, that there are so many analogues of Koska numbers, and I think we need to work and figure out what is the real relation between them. I don't know. So, but let me explain the Koska numbers. So P lambda, of course, is our Mcdonald polynomial. And the first thing you can try to do is to expand it in terms of monomial symmetric functions. So that's just a monomial expansion. That's what everybody wants to do when you first look at a Mcdonald polynomial. And this already gives you some analog of Koska numbers. So this generalizes the formula which we write sure function as a sum of monomials. And these K lambda are the ordinary Koska numbers. So here, I mean, this is the Mcdonald polynomial, symmetric Mcdonald polynomial. And this is the Koska number, classical Koska number. Koska. This is a monomial symmetric function. Symmetric function. And this, of course, is a sure function. And these Koska numbers are representation theory combinatorics are incredibly important. So that's the first one that one would think of. And I'll explain how to give a combinatorial, I'll explain Mcdonald's combinatorial interpretation of these numbers in a moment. So the second one, which you can do, is you can take the elementary symmetric function and expand it in terms of Mcdonald polynomials. So I wrote it, I tried to, not sure. So we'll call that K lambda mu 2. And this is a sum over lambda now. So this generalizes if I take the elementary symmetric function and I expand it in terms of sure functions, then I get the ordinary Koska numbers if I have done it correctly, all the conjugates. So mu dash.
Time, do you mean the conjugate of?
Yeah, mu dash is the conjugate partition. Partition to mu. And E mu dash is the elementary symmetric function. So in the classical case, these are this. Oh, I should remark that this happens when Q equals T, and this specialization is also Q equal T. So if I take the QT Koska number and specialize Q equal to T, it will turn into the ordinary one. But a priori, well, these two generalizations already are not the same. And we need to write down better what is the relationship between them. So the third one is if I take G mu, and I will explain in a moment what the G's are, and expand those in terms of Mcdonald polynomials. So this generalizes the case of the homogeneous symmetric function. When I expand it in terms of sure functions, then I get the usual Koska numbers. So in the classical case, you always get the same Koska numbers. So this H mu here is the homogeneous symmetric function. Homogeneous or complete.
Sorry, and the G mu is a polynomial. It's a function of x as well as q and t, or just x? Or?
Yes. So let me say, so G mu, you're asking about G mu?
Yeah, because the E mu and M mu, M lambda were, sorry, M mu were functions purely of x, right? Without
So maybe a quick way for me to define G mu, I'll define it more thoroughly in a bit later, but GR is a polynomial on x1 up to xn, and q and t, and this is times p of a single row. All right, so it's essentially the Mcdonald polynomial up to a constant. It's the Mcdonald polynomial for a single row.
Okay.
And so then I multiply those together several times. So then I can define G mu to be G mu 1, G mu 2, up to G mu L. And that gives me a basis. Again, you look for the transition matrix between the G basis and the P basis. And this gives an analog of Koska numbers again, QT analog.
Excuse me, what happens if you put H mu instead of G mu?
You mean if so your question is what is H mu expanded in terms of
yeah,
Mcdonald? I don't know. I don't know at all.
that's another analog, right?
That should be another analog. Yes, absolutely. So I really don't have any idea what it should be.
I was just wondering why G mu, but I guess yeah.
So yeah, that's a good question. Why G mu? That one I can answer. So this is this comes from the horizontal strip Pieri rule. Pieri rule. And this one comes from a vertical strip Pieri rule. So in the Mcdonald polynomial case, we have some Pieri rules for multiplying by a single row or a single column, and these are coming from the E's and the G's. So this is the reason why I chose those. Okay, so the fourth one is the one which I mentioned last time, which is if you take P lambda in QT, then you should expand in terms of P mu in QT, and this gives another fourth analog of Koska numbers, which I think is very interesting. So the reason for this one is that this comes from the Val character formula. And this generalizes the S lambda equal to the sum of K lambda M mu, but this time at a different specialization. This is when T equals 1. You get that. And we'll see how the time goes, but at the end, maybe I'll explain some more about why this is particular. I talked last time about why this is interesting, but there's even more reasons. So the final one is Mcdonald's. So Mcdonald himself has a generalization. Mcdonald's K lambda mu QT. And the way he does that is he writes J mu QT as the sum, I'll call it K lambda mu 5 of big shores. So J mu is equal to a constant times P mu, I'll make that explicit in a moment. And these functions are called the big Schurs. And so I will also, so this is, if you like, the outline of the plan for today. I just want to explain what all of these different parts are, what they are. So eventually I'll tell you what the big Schurs are. So the first thing I want to attend to is this constant. So this constant is called a hook number, QT hook. This constant. And so let me define it carefully, because these QT hooks really control seem to control the combinatorics in several ways. So QT hook numbers. So lambda, of course, in my mind, lambda 1, lambda 2 is a partition. So it's non-negative integers which are decreasing. And I always think of lambda as a collection of boxes. So lambda R boxes in row R. And I can also write it in terms of columns. So lambda C dash boxes in column C. So if we make an example, you would have something. This, like this. Okay, so how did I do? So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes in the first row. And I have 1, 2, 3, 4, 5, 6, 3, 1. So lambda itself would be 10, 6, 3, 1. And then I have in the column, I have 4, 3, 3, 2, 2, 2, 1, 1, 1, 1. So lambda dash is this 4, 3, 3, 2, 2, 1, 1, 1, 1. Okay, so a box for me is then some box in this diagram. This is in row R and column C. So this is R equal 2 and column 3. So whenever I have a partition, so if I have a partition and a box there, then these lengths are the crucial lengths. So this, so you can see here, this is R, this is C. This length here is called the co-leg. So I'm following Mcdonald. So the co-leg is R minus 1.
Other way around, right?
Yeah.
C should be R and R should be C.
Why? R is the row. Where should it be switched?
Oh, no, fine. Sorry. Go ahead.
Yeah. Okay. And this one is the co-arm. So this length is the co-arm of B. So this is C minus 1. And this length is the leg of the box. So the box is B. And the leg of the box is lambda R. So the length of the first row, of the rth row, minus C. And this length is the, oh, sorry, I got it. This is arm. This is arm. And then this length is the leg of the box, which is lambda C prime minus R. So we have all of these things. Okay, now the hook numbers, these are the crucial numbers. So my partition is called lambda, and the hook number of the box B is, so I imagine it this way, is that I take my box, which is here, and then I put for that box, I put for the lower hook, I put T down like this. So this is the box. And I put Q across like this. And so the hook number then is 1 minus Q to the arm, T to the leg, plus 1, because I put also a T in the box itself. So not only T's in the leg, but also a T in the box itself. All right, and upper hook is very similar. So we take the partition, and in the box, that's the box there, we put Q's across for the upper hook and T's below for the, and so the upper hook is 1 minus Q to the arm lambda B plus 1 and T to the leg lambda B. Yeah. So I hope it makes sense what these are. So I can define the lower hook of the whole partition is the product over all the boxes of the lower hook of each box. And the upper hook of the whole partition is the product over all the boxes of the upper hook of the box. So you just, okay, now I can write down the constant very precisely for these J's. So the J's are none other than the mu's, but the difference is this, the J's are none other than the P's. The P's are the Mcdonald polynomials. And these are called the integral form. Integral form of Mcdonald. And it's really quite amazing, because all I did was make this small transformation, and so we can copy that here. Yeah, so I can erase this now. And once you make that transformation, then the J's, or no, well, I think it's proved now. These have a monomial expansion, have coefficients in just polynomials when expanded in terms of monomials. In terms of ordinary monomials, x1 to the mu1, xn to the mu n. So normally when we looked at Mcdonald polynomials, they always have these horrible rational functions on the numerator and the denominator. And somehow this small factor, which we are seeing here, corrects for all of that. Another thing I wanted to, while I'm thinking of it on these, we gave 5 analogues of Koska numbers. So another problem is, so let me just state it as a problem. So we have 5 analogues. Of Koska numbers. are there partition function formulas? Function formulas. So in the classical case, Kostant had given a very beautiful formula for the k lambda mu as well. I won't remember it exactly, but it's something like the sum over the symmetric group of -1 to the length of w, and then there's a certain partition function, and then some number which I won't remember, something like w lambda plus rho minus mu plus rho. So this is called the partition function formula. It's an alternating sum formula, and you would like to have some QT analog of this in all of the cases, and I really have no idea how to build those. Okay, so let me tell you now about the expansion. So let's go back to the very first analog, which is this monomial expansion, and we'll study that. Okay. So a pair of partitions, and this is, even if you don't know the classical combinatorics, I'll show you. So a pair of partitions, and I'll write lambda slash mu, that's the usual notation. So this is called a horizontal strip. Horizontal strip. If lambda c dash, so that's the length of the column C, minus mu c dash, that's the length of column C and mu, is either 0 or 1 for all C, for all columns. Okay, so that's a horizontal strip. In our mind, it looks like some collection of boxes like this. The inner partition is mu, and the outer partition is lambda, and this purple, this shaded part is lambda slash mu. So that's what a horizontal strip is. And if I'm given a horizontal strip, I can define the following number, which is psi lambda slash mu is equal to the product over the boxes in, so each box, of course, for me is a row column, and so I look at a box in lambda. So in my mind, I'm looking at a box, say here, like this, and that's in row R and column C. And then I want to make sure that it sits inside that the horizontal strip sees it in its arm. So I want this arm to touch the horizontal strip, and I want this leg not to touch the horizontal strip. So this is the kind of box. So I'm going to take the product over all such boxes, and take the lower hook of the partition divided by the upper hook of the inner partition times the upper hook of the outer partition divided by the lower hook of the outer partition. Okay, so I know an amazing number. I'll just note that these, because of the way this is built, this psi lambda slash mu well, in fact, whenever Q is equal to T is equal to 1. Because when Q is equal to T, the upper hook and the lower hook are exactly the same. So if I take the lower hook divided by the upper hook, then they cancel because the numerator and the denominator are the same. Okay, so when Q equal to T, they're the same. Let me do an example of how we built a standard tableau. So what are called, I guess many people call them semi-standard Young tableau. I would like to call them horizontal strip tableau. Of shape lambda and type mu. Type nu. So I don't like the word semi-standard Young tableau, because if you never seen one before, it doesn't mean anything. Semi-standard could be anything. But horizontal strip tableau really tells you that it's built from horizontal strips. So an example of a horizontal strip tableau is first I put one horizontal strip, and then I put another horizontal strip, and then I put another horizontal strip, and then I put another horizontal strip, and then I put my final horizontal strip. And so this is an example of a horizontal strip tableau. This one has shape of the tableau is 10, 6, 3, 1. And the type of the tableau, there are 4 ones. You can see here there are 4 ones, so that's 4. And then there are 4 2s to make a horizontal strip, so that's 2. And then there are 3s which make a horizontal strip, so there are 5 3s. And similarly,
that should be 4, right? That at place up 2.
4, yes, thank you, 4, yes, 4, 5, and then there are 3 4s and 4 5s. Okay, so that's a horizontal strip tableau, also called a semi-standard Young tableau. And lambda is the union over all possible types. So this is just a set of all horizontal strip tableau. Filled from 1 through n. Because I have in my mind, I have fixed in advance, I have fixed the number of variables in my Mcdonald polynomials, and so
I think you need
I don't.
a subscript of new on the.
Yes, thank you. Great. Okay, so we have defined, and the reason I use this notation of B lambda for this is because this is a crystal, and I think that one of the problems with Mcdonald polynomial theory is that we don't yet understand how the crystals help to do Mcdonald polynomial theory. So I want to try to push towards the world of crystals by thinking of the horizontal strip tableau as the elements of the crystal. Okay, so of course I can think of a tableau as a sequence of horizontal strips. So first I have the ones, and then I add to the ones, I have this many boxes after I take, so this is all the boxes less than or equal to 2. This is all the boxes less than or equal to 1, and so on. So I can always build a sequence of shapes, and the sequence of shapes is equivalent to the horizontal strip tableau. This is essentially the same data as what's sometimes called a Gelfonsetlin pattern. Okay, so once I write it this way, then associated to a horizontal strip tableau, I can define the product over the horizontal strips that make the horizontal strip tableau of these hook numbers. So this is the product over I going from 1 to n. So let's copy the hook number just so that we remember. So this is the hook number for a single horizontal strip. There. And then we can all the horizontal strips that make the whole tableau, we can take the product over all the horizontal strips that make the whole tableau. So that's where. Okay. So this is a
So, hello,
combinatorial.
sir.
Yeah.
So when psi we calculate when mu is a empty partition, like if we take here I equal to 1. So we are
Then
subtracting empty partition. So
then the hook numbers should be 1. So
Yeah.
so whenever I haven't defined it, where did we define the hook numbers? So here I should put that if B is not in lambda, then the hook number is just defined to be 1.
okay.
And similarly, I'll put it here. And that way, if the mu is the empty partition, then this factors will just be 1. All right, and so we make that convention to make the notation better. Is
Okay.
that good? Okay, great. So now we could make a wonderful definition. We could just forget all of our previous theory, and we could define the Mcdonald polynomial to be the sum over all the horizontal strip tableau of this constant that we have just defined, psi t, times the monomial, where xt means x1 to the number of 1s in t, x2 to the number of 2s in t, and so on, n's in t. So now you have a definition, a purely combinatorial definition of this. And you are in the same position that Stanley was in 1970 or something. That you have a purely combinatorial. So in the case of the short function, this was historically very important. So if q is equal to t, what you get is that this is just the sum over all the costs, or the sum over the crystal of the weights of the crystal. The weights are, and this is, of course, one of our favorite definitions of the Val character or of the Schur function. But now we have immediately a problem. So question. With this definition, P lambda as of course, if we go from Daha or from some other theory, then of course we know that P lambda is a symmetric function. But with this definition, it's not clear at all. You have to show somehow that that these constants that these constants are somehow symmetric under the permutation of the variables.
Hello, sir.
So yeah,
Can I ask one question?
yeah.
So for this Schur function, we know we have key polynomial, right?
Yeah.
So is there similar version in P lambda? Is that something interesting or?
Yes, it is very interesting. So the key analog of the key polynomial is in fact the non-symmetric Mcdonald polynomial. Yeah. And there is some version of a similar definition. So, but it needs cleaning up. What shall I say? There is some partly analogous definition of the key polynomial of E mu in such a way that you can add up the E's with some constants, in the same way that you can get key polynomials to generate Schur functions, you can get the non-symmetrics to generate the Mcdonald polynomial. But the combinatorics I don't understand at all. I think it's so studied.
Sorry, is that mu
And,
a lambda?
Sorry?
Is that mu a lambda?
Lambda. Sorry, lambda.
do we know the effect of crystal operations on the statistic?
No. So that's another question that I would love to understand. And that is that, so let's let E0 tilde, En tilde, sorry, E1, it should go from just 1 to n minus 1 in this case. F1 up to n minus 1 be the crystal operators. And that is then compute simply this number that if I apply a crystal operator to the tableau, how does that relate before I apply the crystal operator? And I don't know. These are, I think actually there's a lot of gold here, very close to the surface, and you just have to start to get to work and compute your hook numbers. I don't know. Okay, so that's great. So we have lots of questions already just for the monomial expansion. Now let me talk about these Pieri. Let's talk a little bit about, well, maybe I'll just grab this Pieri rule as a heading. Oops, I don't know what I did to that. Hopefully I can paste it here. Yeah. Okay, so how do the Pieri rules work? Well, so first let me define the elementary symmetric functions, E0, E1 up to En, and these generalized homogeneous symmetric functions. And these can both be defined by generating functions. And that's probably the best way to define them, I guess, because it shows their structure in a very good way. So if I take the product I going from 1 to n of 1 plus xiz, and then take the coefficient of z to the r in this product, then that's the elementary symmetric function. And in a very similar way, the GRs can be defined by a generating function where you have the product over the variables of t xiz q infinity divided by xiz q infinity. So this for any variable, so y q infinity is defined to be 1 minus y, 1 minus qy, 1 minus q squared y, infinite product. But it doesn't matter that it's an infinite product, because the more factors you take in the product, you're only taking the coefficient of z to the r. So you can always just compute this coefficient of z to the r with only a finite number of factors. So it's only finite product here. So that's not a problem. These are very well defined. And so I can define also E mu dash to be E mu 1 dash, E mu 2 dash, and so on, and G mu, G mu 1, G, and so on. Okay, so the E's, they correspond to vertical strips. So E's is for vertical strips. Let's say it this way, corresponds to vertical strips. So it's just like we had before, except that now the strip is this way, forming a vertical instead of horizontal. So the GRs, they correspond to horizontal strips, which we talked about already, which are like this, some horizontal strip with the mu and lambda. Okay, now here we are going to define some similar Hooke numbers. So for vertical strips, we define H lambda slash mu to be the product over boxes. So again, I want that when I look at the arm, I don't see the, so I want something like this, where when I look at the arm, I don't see the horizontal strip. And I want it when I look at the leg, I do see the horizontal strip. So this kind of a box. I'm taking the product over such boxes. And then we take the lower Hooke lambda of B divided by the upper Hooke lambda of B times the upper Hooke mu of B.
Sorry, one of them is a not equals, right?
One of this is a not equals. Yeah, I wanted to see the, yeah, just like in the picture. The picture is, and then the Hooke number. So these are the Hooke numbers again for the internal and the out and the exterior partition. So that's the case for the vertical strip. And for the horizontal strip, we have a similar number, which is the product over all the boxes, which don't see the horizontal strip in their leg. So I could have a box like this. That's okay. I could also have a box, say like this. That's also okay. That the arm doesn't matter in this case, but only the leg. But I must see the horizontal strip in the leg. And then we take again this Hooke number times H upper Hooke mu divided by H lower Hooke mu. All right, so these are, again, completely explicit constants for in terms of the partition and the horizontal strip. And now we have these beautiful rules proved by Mcdonald, which says that if I take an elementary symmetric function, then I get times a Mcdonald polynomial, then I get a sum over all possible vertical strips of length with R boxes, of length R, of R boxes. So I want the number of boxes in the strip to be R boxes times this constant that we just defined, psi lambda prime times p lambda. Right. And finally, I take GR times P mu. This is the sum over horizontal strips of R boxes times phi lambda slash mu of P lambda. All right. So using these rules, you can compute completely this decomposition, because you can do it iteratively. You can do the first GR times the empty partition, and then the next part, and then the next part, and you can compute what these Koska numbers are. And we don't know much more about them. So there's many questions to ask here as well. All right. Now let me go to the fifth one. How am I doing? Yeah, we're getting, so the fifth one here. So this is Mcdonald's KQT. And I'll tell you the parts of this. Okay, so we find that this J mu was the lower hook mu number times P mu. I think that's, yeah. And so that's the definition of J. So I need to tell you what these big Schurs are.
Sorry, one question. So then the two formulas you wrote above generalize the usual PRE rules.
Generalize the usual PRE rules.
Or
That's
specialized
right.
even, right? Okay.
That's right. For multiplying by Schur functions, yeah.
Right, right.
Yeah. Okay, so the big Schurs. So I must admit that, you know, when I learned symmetric functions, I ignored these big Schurs because I didn't see the importance of them. And I now am convinced that was a mistake. I should have paid more attention because these are something is amazing about them. I don't understand them very well. So here is a way to write down the big Schurs. So I'm going to define now broken border strip tableau. Border strip. Before we had horizontal strip tableau, now I'm going to define broken border strip tableau of shape lambda, lambda, and type mu. And the idea is so let me draw one to start, and that is, so we start with the empty partition. So we start with the empty partition, and then I'm going to put a border strip. So in this case, I'll put 3 1s and a 1. So that's my first border strip. Maybe I'll and then I'll go to the next one before I explain what the rule is for a border strip. So here, this is a border strip. And we can see it. So what did we get? We took the old partition and we added, in this case, we have added these blue boxes. So I want to divide this into 2 connected components. And what is it? The rule for a border strip? Well, I think of these diagonals. And of course, I could tell you the partition by telling you the lengths of each diagonal. I number the diagonals this way. And if I tell you are in each diagonal, I tell you the part, okay? So a broken border strip has it so that the lambda of a diagonal, so the length of the diagonal minus the length of the previous diagonal is in 0, 1 for each diagonal. D. So a broken border strip. Is lambda slash mu such that. Does it make sense? What is a broken border strip? That I can just go along each diagonal and I can add at most one box. And of course, the outer one must be a partition and the inner one must also be a partition. So here I can add some 3s like this. So this one would have shape of T is 1, 2, 3, 4, 5, 6, 3, 3, 2, and it would have type of T is, so I had 4 1s and I have 1, 2, 3, 4, 5 2s and I have 1, 2, 3, 4, 5 3s. So each broken border strip tableau has a shape and a type, and I could define a broken border strip crystal. Well, I could define the set of all broken border strip tableau as the sum of these. So this is the set of all broken border strip tableau. Okay, so now we define a statistic on these. So the statistic is as follows. If you have a single broken border strip, so if lambda slash mu is a broken border strip, then we define chi lambda slash mu to be 1 minus t to the number of connected components. So I'll write connected components. And then for the product over the connected components of minus t, the number of rows minus 1. So each connected component looks something like this. That's a single connected component. You can travel just by steps that move right or down and traverse component. And the number of rows is just this height. This is the number of rows. So if I take the number of rows minus 1, then this gives me a statistic. Okay. So, and then for a tableau, I can, just as before, take the product over all the successive strips of the weight of each broken border strip. Does it make sense? So somehow before we were doing horizontal strips, and then we were doing vertical strips, and now we're doing diagonal strips. And that's otherwise the theory is quite the same. Okay, so now the big Schur functions are the following symmetric functions. Big S is the sum over all the broken border strip tableau of shape lambda, chi of the tableau, x to the t. So as before, x to the t is x1 to the number of 1s in t up to xn to the number of n's in t. And as before, with this definition, you have a problem, and that is you have to show that these S lambda are symmetric with this combinatorial definition. There are of course other definitions. You can look in Mcdonald's book, from which it's more obvious that it's a symmetric function. But if you look at the other definitions, it's not so obvious that it has this combinatorial expression. Okay, so now I'll remind you, Mcdonald's says that we should take these integral form Mcdonald polynomials, and we should expand them in terms of the big shores. And the conjecture is that, so the conjecture is that there exist statistics, let me call them shift mu and charge mu, T, such that this K lambda mu 5 QT is equal to the sum over T standard. So standard of shape lambda lambda of Q to the shift, mu shift of T, T to the mu charge of T. So standard means filled with 1, 1, means that it's type 1, 1, 1, 1. And horizontal strip. So in other words, you have to do, it's increasing in rows and increasing in columns, and there's just filled with 1, 1, 1, 2, 1, 3. So let me just write that, increasing rows, increasing columns. Of course, the number of standard Young tableau of shape lambda is the dimension of the irreducible representation of the symmetric group. So one of the consequences of this conjecture is that K5 lambda mu 1, 1 is equal to the dimension of the irreducible representation of Sn labeled by lambda. But we have no idea, at least I have no idea how to prove this, how to understand this conjecture. This is Mcdonald's prediction.
So you also want a sum over all mu, right?
Sum over all mu? No. Where?
No, I mean, there's no mu dependence on this.
For each mu. So for each mu, the specialization at 1, 1 should be the dimension of S lambda, Sn lambda.
Oh, it holds for every mu. I see. Okay,
That's right.
Thanks.
Which is amazing. I don't.
I mean,
Yeah.
the statistic itself depends on mu, right?
Sorry?
The statistic itself depends on mu.
Yes. Yes. The statistic itself will have to depend on mu. Absolutely. Yeah. That you can see from just a few examples.
By the way, in the statement above, Arun, when you said, sorry.
Which one?
So the big shores only have a T in them but not a Q, is that right?
That's right. Big shores only depend on Q. Sorry, that's right.
T, yeah.
So this is a function of x1 up to xn and t. There's no q at all in them. Yeah. So,
Okay.
yeah. And these are extremely fascinating numbers. But I cannot say I have any understanding of them. All right, I should stop there for today.
Any questions or comments?
Could you scroll down to the end?
Who made this conjecture? Was it McDonald himself or Slade?
Yeah, it was Mcdonald. And then very shortly afterwards, there was another conjecture of Heyman, Garcia and Heyman. They have another conjecture. So they constructed explicitly a module, constructed a bi-graded SN module, such that if you take, so that module, let's call it GH mu, such that if you take GH mu and you look at the graded character of it, then it's the direct sum over lambda of Sn lambda, where this appears in degree and okay, so in other words, they don't know how to compute shift and charge, but they know that when you do compute them, they will be the degrees in which the irreducibles appear in this Garcia-Heyman module. So, but that came just 1 or 2 years after Mcdonald's original positivity conjecture.
So how does this fifth one specialize to k lambda mu?
Well, k lambda mu at the value 0, 1, the original k lambda mu. Perhaps more importantly, k lambda mu 5 at the value 0t is the Koska-Folks polynomial. Yeah, so.
So do the others also give me Koska-Folks polynomial and that specialization?
I don't know. I don't see any reason why they should, but on the other hand, I don't see any reason it should be true either. So I don't know.
Yeah.
But this fact is already proved by Mcdonald. So this is definitely true. I just don't understand what's really causing it.
Okay.
Any more questions? Okay, if not, let's thank Arun.